thumbs up when it's on.
Okay, good afternoon, everyone. Today we have Megan Kreiger. Let me close this door. So today we have Megan Kreiger. She is a mechanical engineer at the Engineer Research and Development Center, CERL, from the U.S. Army Corps of Engineers. Her current research work includes the research and development of an innovative, large-scale additive manufacturing approach to the construction of contingency structures. And she is the additive manufacturing lead on the automated construction of expeditionary structures program. She completed her master's degree in material science and engineering from Michigan Technological University with a thesis concerning additive manufacturing under Joshua Pierce in 2012. She also has a graduate certificate in sustainable infrastructure in 2010 and a degree in math in 2009. Let's please welcome Megan.
So I'm Megan Kreiger. A lot of you may be familiar with where I work, but a lot of you may also not be. I work at the U.S. Army Corps of Engineers research branch, which is called the Engineer Research and Development Center. And we have one lab in Champaign, Illinois called the Construction Engineering Research Lab. So everybody calls it CERL. So if you've heard of CERL, I work at CERL. I got involved in this large-scale 3D printing technology about 4 years ago. And we've really come a long way since then. But I'm going to get up into this, and you guys probably find out a lot of information about something that's a little bit different outside of your normal realm. So 3D printing. Most people have heard about 3D printing. They know about the small-scale 3D printers that print small trinkets. How they print is they print layer by layer as they go up to create a 3D printed object. There's a lot of buzz and hype associated with 3D printing in general. From everything from we're going to be 3D printing organs in the next 5 years to put into human bodies, all the way down to we're going to be 3D printing cars for people to ride in, drive in the next few years. It's going to completely change the world that we know. And while a lot of that stuff is true, there is a lot of hype associated with that and a lot of buzz. And that really overrides the principles of 3D printing and what it can actually do for society in general. So when you clear away all that buzz and hype, what you get is you get 3D printing for automotive applications, whether that's 3D printing the actual parts or helping to make the final 3D parts by making all kinds of tooling to create that. All the way to aerospace. Can we 3D print lighter weight parts that we can then put onto rockets or on airplanes that reduce the amount of fuel and basically improve the efficiency of the vehicles that we're flying? All the way to art. You can 3D print sculptures, all kinds of stuff. To biological, yes, there are people trying to 3D print organs. Are they ready yet? Not quite. It's still research. And then you get all the way into construction. So that's where I'm at, is I operate in the construction large-scale realm of 3D printing. So what is 3D printing? There's all kinds of definitions from ASTM as well as from SME. And basically what it comes down to is 3D printing is the creation of 3D objects in a layer-by-layer fashion using automated controls from a computer. So that's different from subtractive, where you traditionally take away material, and so you have a lot of waste associated with that, and limited geometries. The benefits of 3D printing, and I'm talking 3D printing in general, you have everything from speed. So you can now, instead of manufacturing one part, a prototype that will take you months in order to create, now you can create them in a day, a week, much less time. And that applies for a lot of things that you're only creating a couple of. Then there's the single-step manufacture point, where with that, you can actually create a very complicated part without having to reprocess it. So usually if you make a automotive part, you would drill a hole into it, you would tap it, you would send it off to somebody else who would cut another portion off before it goes through multiple steps in order to create an end part, which then gets put with other end parts to create an enormously complex part. With 3D printing, you can just create that in one step, and then you do some nice finishing process on it. Cost. Now cost, for if you're making just a couple of something, it's much cheaper to just produce it one time than to put it through that whole method that I just described before. Risk mitigation. You can now make prototypes that then you can test before you get to the end part, and you can make lots of prototypes. So before you put something in a vehicle or on an airplane, you can run through multiple versions of it and make the best part for the application. Complexity and design freedom. With that one, you can now make incredibly complex parts because it doesn't cost you any extra money to make them incredibly complex. There's no extra tooling required. The cost difference between making a complicated 3D printed part and a standard part could be the same, or it could be just a slight bit higher depending on what you have to do to finish it. Customization. Now instead of just making one very generic part, you can make it any way you want. So one example is there's a company making hearing aids. So they make them to fit your custom ear shape. By taking a multitude of photos of your ear lobe, they can make it so that it instantly fits your ear instead of having to have discomfort just in order to hear. And then ease of access. So pretty much anyone could buy a 3D printer for a couple $100s right now. You won't necessarily get a great quality out of it unless you put a lot of time and effort into it, but they're accessible. So basically you have to understand how to use CAD to model 3D objects or another modeling software, and then you can create these objects out of polymers. And if you get more advanced, you can create them out of different materials. And sustainability. So how this works is that because you're not taking a material like a block of wood and CNCing, removing the portion off the outside, and then having a bunch of waste that you then have to figure out what to do with that material, now you can just create it without making any excess because you can take the paths specific to make the part you want. So you use less materials in the process, which makes it more sustainable. So, small scale printing versus large scale printing. So I'm kind of going through the whole differences of 3D printing just to give you guys a basic understanding of what the differences are. Small scale. So typically a small scale is about 1 meter cubed or smaller. That's what the majority of 3D printers in existence are. You can find them in most libraries, at the university, at all different places across the US and around the world. They typically cost less than $500. But moving up from there, because in order to create something large, you'd have to create a bunch of parts and put them all together. It's much better if you can create a large object all in one go. So a little bit less common is large format additive manufacturing, which is about, it's larger than 1 meter cubed. These printers cost generally about $100,000 or so to buy. And there's people printing automotive parts like the 3D printed cars created by Local Motors and Oak Ridge National Laboratories, pictured here. There's people that have been printing propellers. There's something called the WAM propeller, which is a metal propeller designed for ships. So instead of having multiple parts, you can now create these in one go. Something completely different is what I do, which is construction scale 3D printing, which we describe as much, much greater than 1 meter cubed. There are maybe a couple dozen, if that, of these kind of printers in existence in the world. And so when we talk about hype, especially when we're talking about large-scale 3D printing, it has all the same characteristics of hype from small 3D printing. So a lot of people talk about 3D printing infrastructure is completely going to change construction as we know it. Well, if you look at history and when new technologies come out, they don't completely change everything. Usually what happens, it'll change a subset and then it kind of moves its way forward. But in this industry, there's a lot of sensational news articles and over-exaggerations and hype, as well as exaggerations on the capabilities of where they stand and the difference between print time and elapsed time. So a lot of people will tell you, we printed this in 10 hours, 24 hours. In actuality, they printed that over months or even a year. And so we'll get more into that as we go. But here's just a funny little cartoon, which is basically you forgot to turn off the 3D printer and the next day they come back and it's a skyscraper. That's just an example of the kind of, it leans towards the hype that's in the industry there, and that's kind of the perception that the general public has. So there's something called the Gartner's hype curve, and basically they analyze the state of technologies as they currently sit. There's a period off to the left here, which is the innovation trigger. That's when something is discovered or invented, and it's just beginning to get used and understood. And then it goes through a period of what's called the peak of inflated expectations, which is all the way up here. In that time period, there's a lot of hype. People talk about how it's going to revolutionize everything. Which then, because of that overinflated expectation, you go through a period which is called the trough of disillusionment. The trough of disillusionment is usually where technologies die. It's the point where people have exaggerated it so much that it never actually gets used because people realize that it can't do what people expect it to do. And then this is followed by the slope of enlightenment. If you can get through the trough of illusionment, you can get to that point, and that's where people realize the actual applications of what is being discovered and what is being used, so that it actually becomes a plateau of productivity. So in that area, that's where it's just common practice. This is what is done. So this right here is actually Gartner's hype curve for 3D printing. And so there's different topics that he does all of these curves for. But if you look on there, and you look on this curve, it's kind of hard to read because of how small everything is. On here we've got everything from nanoscale 3D printing, all the way up to 3D printing for retail, and just past the peak is 3D printed surgical implants. And then there's things over off to this side, which is like 3D scanners and 3D printing for hearing devices. So you can see that over here, like I discussed about the hearing devices, having those custom solutions for hearing aids and other things is actually very valuable, and they've put that on this curve to represent that. So where is construction 3D printing? Well, there isn't exactly a category for us on this curve. The best I can figure out is that we fit into macro 3D printing. Seems like a good characteristic for us. So in 2017, they marked us right here, which means we're on the path up to this peak of height of expectations. It's now 2019, so I'm guessing we're about right here, just at the peak or a little bit past. Well, I don't know about you, but this technology that I've been working on, I don't want to see it die. And so how you get through this trough of disillusionment, which potentially we are just about to go through, is through collaborations. And so we have been collaborating with NASA Kennedy Space Center, NASA Marshall Space Flight Center, Skidmore, Wings and Merrill, structural firm out of Chicago. We have been collaborating with Oak Ridge National Laboratories. We've been collaborating with the University of Illinois. And we've been collaborating with Caterpillar, and we're always interested in further collaborations. Basically, we reach out to industry, the construction industry, and we get early involvement from both the general industry as well as specifically for military engineering as well. And so we want to make it past this trough. And so we're moving towards that plateau of productivity. So what is construction 3D printing? So construction 3D printing is exactly what you would think it is. It's 3D printing basically to produce large-scale components, and we use concrete specifically right now, by depositing material in successive layers. So you can kind of think about it like laying bricks of a building or CMU blocks, only it's concrete in one single bead as we continue to go up. So some of the people who've fallen victim to the hype curve, or to the hype examples that I was giving before, that you may have heard about because they did hit news headlines and they were known all across the US, is MX3D. So about, I think it was the year 2015, they came up with this concept of taking robotic arms and welding a bridge across the canal, connecting together. And so everyone was talking about how, oh, have you seen the news? They're already doing this. People are already printing metal bridges across canals. But it was just a concept because that was what made it out to the media. And it was a very interesting new concept. Well, if you flash forward to this year, they finished the bridge. They didn't print it across the canal, they printed it in a lab with a robotic arm that printed it welding in successive layers. But the difference there is that when you look back, people still think that this happened years ago. And so this bridge is supposed to be installed this year. And so it kind of gives you a perspective of, a lot of people talk about things that they're just starting to think about or have just started to work on. And then it spreads into these unrealistic expectations of, when are we going to see 3D printed metal bridges? Is it next year, the year after? When really it's just being developed. And so these things are coming out years later after people mention them. Another one is Apis Core out of Russia. They had news about how they 3D printed a building in 24 hours. And this is similar to our concept where you print in cementitious material, layer by layer until you get to the top. Unfortunately though, this building, as well as the next one I'm going to talk about, weren't printed in 24 hours. So they were spread out over weeks or months of time to actually get to the final result. So when people talk about this building is printed in 24 hours, when are we going to see 3D printed buildings day after day coming in the future? How many buildings can we create, in a week? Let's try to print a bunch of them. And Icon, they are based in the US, and they had a similar issue where they had a lot of news get out about how they had 3D printed a building in 24 hours. And it said it was a 700 square foot building that only cost $10,000. And there was all kinds of other information about it. But when you dug deeper, that was their concept. So when they said, we could in the future potentially print a building in 24 hours for $10,000 at 700 square feet. But what they actually did was printed a building that's about 350 square feet approximately. And they printed it over a series of a week or more. And then I'm not sure about the cost itself. So when you start looking at the details of what people are actually doing, it's very different from the concepts that you're seeing in the news. What is interesting though, is the actual real meat of what's underneath. So under all this hype, like in this example, the world's first 3D printed bridge, it was printed in what's called a powder bed fusion type process. So basically it's a bed of powder, cementitious type, that you put a binder on to slowly build up the material, and then you pull out all the material that doesn't have binder on it. And the interesting thing about this is the only thing people really talked about with this bridge in the news was they 3D printed the first bridge. It's very exciting. World's first 3D printed bridge. For engineers though, you look at this design and you say, how would you produce that using conventional techniques? It's an optimized geometry, when you look at how they actually got to their model, their final model, that's not a typical construction process. So what 3D printing can actually do for the construction industry is give the ability of freedom of geometry so that people like architects can actually see their visions come true of what they want. Or structural engineers can actually design a structure to be structural where they want it to be structural. Or, the transportation engineers can then design their elements to be exactly what they want it to be. So you can apply these different concepts to your specific field, and it gives the field a new creative component with construction. Because typically, when you come up with a design like this, people go, "That's awesome, that's great, that is a great concept." But then they say, "That's too expensive, because it's gonna cost us that much more to make formwork or that much more to do X." And so this happened again recently with the world's longest 3D printed bridge that was just earlier this year. And it's the same kind of idea, is this geometry would be very costly to make using conventional technology. And it claims to be the world's longest 3D printed bridge. But actually, when you remove all that concrete, there's a steel bridge underneath. So when you start talking about what defines a 3D printed bridge, right? Are we talking about the structure of it, or are we talking about the visual appearances of it? As well as what can it give us? Because if this is essentially a nice facade, it can give us nice facades. It definitely can. As the Construction Engineering Research Lab, we're interested in the structural. So we are not too concerned currently with the prettiness of what we make. What we want to make is something that's strong, and we want to make something that we can print using local materials. So we like to call ourselves the large-scale additive construction technology. Our tagline is basically, we demonstrate and test the capability to print custom-designed expeditionary structures on demand in the field using local available materials, which includes making things like buildings, obstacles, bridges, fighting positions. And the reason we do this is essentially to save lives of our soldiers and the civilians by reducing the amount of personnel it takes to do construction, the amount of material it takes to do construction, as well as the logistics of getting both personnel and material and all kinds of other technologies up there to do construction. So this is, right here, a picture that shows a lot of the stuff that we've done so far. And I'll get into more details later. But basically, what I want to tell you is it's not just buildings, and it's not just bridges. It's infrastructure. Civil infrastructure, period. Anything you can make out of concrete or other materials, if we start talking about 3D printing other materials, can be made using 3D printing. Will it be the best method for that application? That has to be tested. We have to see, we have to do the science and the engineering behind that to figure out what the best applications are. So where do we start with this? So we start with basically the design and construction considerations. This comes from everything from developing codes and standards to the actual design, all the way to what kind of construction type are we making, how are we reinforcing whatever structures we're making, and how do we build with these structures. If you make new and wild designs, how are you to tie that to the foundation? How are you to tie that to a roof of a building? What kind of geometries are best for these applications? How much does it cost? What kind of testing do we need, and how do we do quality assurance? So design. What we're currently working on is with ACI, the American Concrete Institute, as well as the Transportation Research Board and ASTM on developing different standards and being part of different committees to make sure that 3D printing for construction is being properly represented as far as what do we think the applications are, how does the print methods actually work, how do we develop testing standards to make sure that we're getting the results that we expect, And how do we standardize across the board how to do structural reinforcement as well as testing? So currently, none of this is specified in code, and it all has to be tested in order to be approved for infrastructure. Now, one of the biggest problems in construction is construction delays. There is a report from 2016 that basically says construction disputes cost approximately $46 million a year, I believe is what the number is. And each time there was a dispute, the average time was approximately 15 and a half months. So if you think about that from a construction aspect, and then you driving down the roads and you're like, that building looks like it's being built for years. If we can reduce that by making some of these processes all-encompassing, like how 3D printing has worked for manufacturing, we can start to reduce those amount of disputes and the amount of delays with construction, because things will be built as expected. There are a couple different construction types that are being defined across the construction 3D printing world. So in normal concrete, you have precast concrete, which is basically concrete cast elsewhere from where it's being put in. Similarly, we like to call, when we do something doing the same process, so say if I was to print back at Searle something and bring it here, that would be pre-printing. Similar to precast, trying to keep kind of a similar vein of the technology there. And then also for cast in place concrete, which is typically concrete that you cast exactly where you want it to go, we call that print in place. And so for pre-print, that has less variability, right? We talk about we're printing in a lab type environment or a factory type environment, and we just build it. We don't have to deal with weather. We don't have to deal with all kinds of variation in materials. We know exactly what to expect, but we have to deal with the transportation part of that. How do we get it from A to B, and how much does that cost, and how sustainable is it? Print in place has higher variability. If we're printing in place, we're printing out in the weather, unless you put up a tent, and then you have to include the cost of setting up a tent, and the cost of taking down the tent, as well as the cost itself of the tent. There is higher variability. So we've got rain, snow, wind, all kinds of things can affect your materials as you're printing. We typically do print in place. We do every once in a while pre-print things. We just recently printed some beams and columns for the U of I to test as part of one of the courses in the civil engineering department. But typically when we're doing a structure, we print in place. And so when you're doing 3D printing processes, you kind of have to have a different thought of how you construct a building in your mind. Typically when you model a building or another structure, you think of it as a 3D model, and you give that in all different kinds of viewpoints with how to build it instructions to who's ever building it, your contractor, etc. Now, with this, you think about it in layers. So if you looked at this room around us, right, and you look at it, pretend like it's a 2D view that you're looking down on, you now have to leave a gap for the door, right? And a gap for that door and that door. And as you go around, that pattern is the same up until you get to about the window, right? And now we have to leave a gap for the windows as we go around and print layer by layer. And then as we get to the top portion of the wall, it's a solid portion that goes all the way around. So when you think about it that way, you now have to consider things like overhangs. So overhangs in 3D printing or structural engineering is when you have something that overhangs the bottom layer. So it would be like when we're printing for this window section, how do we do the lintel over that window, the header lintel, not structural. And so you'd have to put some kind of support or support material in there to be able to print that geometry if you're printing out of concrete. So it's a very twist on design. So you can do a small amount of overhang, but you can't do a full gap like for a window unless you have something there. And so when you're talking about designs, you can kind of see here, this was a original concept for our first building that we did. You can see that we've left gaps for the doors as well as the windows, and it differs in geometry slightly as we go up. So this is fairly typical for the construction 3D printing industry, is you see these kind of 2D views that don't change a lot, that leave a few spaces open. And you see more of the full 3D changes actually in Europe. And so we'll get into that a little bit more later. So what have we done that's different? Why am I up here talking to you? So we've done a number of structures that we've 3D printed. And our mixture that we use is concrete. We use 3/8 inch aggregate, and sometimes larger than 3/8 inch aggregate, which only a handful of people around the world do. Most of the industry uses mortar or paste, or potentially geopolymers, things that don't have large aggregates. But with that, you have the increase in cost. And so what we want to try to do is to use a traditional type concrete, because it will already be accepted in industry, because it's just concrete. 3D printing is just a method, like it's a different method of construction. And so what you want to do is you want to get into the industry with a material that they understand, and then develop it as they start to accept the process. And so what we did is we printed, this is 2 years ago now, we printed the first full-size 3D printed building in the US out of concrete, or any kind of cementitious material. And when we did this, we created basically a rectangular structure that looks exactly like any other building. And one of the reasons we did this is because we wanted to show we can already do what's been done. And when you think about the military likes uniform boxes, the status quo. And so we printed what we call a barracks hut, a B hut, which is 32 foot by 16 foot by 8 foot tall. And we anchored it to the foundation using traditional techniques, as well as we put on a wood truss roof. So you don't have to 3D print everything when you talk about 3D printing. You can use it where it makes sense and use traditional methods where they make sense. And when we printed this, our print time was 21.5 hours. But that print time was spent over months because it was researchers printing week after week trying to print this building. Now, the reason for this, for the military, is that current construction takes about 4 to 5 days for them to produce a shelter for themselves, a solid shelter. And that takes about 8 people, and it takes 5 tons of material, and there's waste, and they have low R values, so the buildings are inefficient. What our goal with this first project was to be able to produce a structure in a day, because that's what everyone had talked about was possible. We wanted to see, is it possible? And we wanted to be able to build it with 3 people and reduce the amount of material as well as the amount of waste and create a more efficient building. And so we, in this process, developed our own material, which we've patented. And the reason for that is to keep it safe for the government so no one else can patent it. And we successfully printed the first building in the US, but it did take us weeks to months. So 21.5 print hours, right? But weeks to months to actually complete because we were very new to this. The next step there was to go and test this someplace that wasn't at home. And so we went to Fort Leonard Wood and in Missouri, and we printed with 2 groups of soldiers. And we trained the first group of soldiers on how to operate the equipment, and the second group of soldiers came in a day later, and I didn't train them. The other soldiers did, which means that the technology that we're working with can be easily transferred to soldiers and Marines and construction workers. And so what we did is we used materials that were from the local environment. We used their local gravel, their local sands, anything that we could obtain locally. With, of course, the end goal being that one day maybe we can use the on-site materials, dig them up, and print with them our whole building, so we don't even have to bring very much with us. And basically we were at this site for 3 weeks and experienced all kinds of weather conditions. So when we talk about on-site printing, we experienced snow and freezing conditions. There were days we couldn't start until 10 because it was below freezing. There were days where it was so windy that we were hesitant to print things. There were days it was raining, and there were days it was super hot. So we experienced all kinds of weather, and in that, we realized we can actually do this in all kinds of weather, as long as we implement a lot of different practices, as far as you don't print in pouring rain, you know? You wait until it's just a light drizzle or so. So this also depends on what you're making. You can see from these pictures, we're not making buildings, we're not making bridges. We're making, this one is basically a mock bunker that you would flip upright and you would have a shelter, or it'd be a fighting position, as well as here we've got like a T-wall where you can make Jersey barriers, we make culverts, all kinds of stuff. If you're talking about smaller components, you can actually print them in different kinds of weather conditions as long as you monitor those weather conditions. And in this demonstration, we actually had a request from the soldiers. They said, can we make a fire pit? I said, sure. So we modeled it up and we printed it on site. And another thing was, this was not modeled before we left Champaign. The soldiers had requested us to print that. We got a picture of what they wanted to make, and we printed it the very next day. So it's one of those things where if someone has a custom solution for something, you can try it. You can print these things and see if they work for your applications. And one of the most important parts of all of this is reinforcing. So this is a part that a lot of people don't talk about with 3D printing for construction. You can use conventional reinforcement for 3D printing for construction. It's very similar to using precast or CMU block type construction. So basically you can leave a cavity. If you're, say, printing a building, you can leave a gap in your wall that you can put vertical reinforcement into and then backfill that with concrete and basically use it as formwork that you never have to remove and actually add structural characteristics to your wall. You can print sections that you can then just consolidate where you want to fill things. So you can make structural portions of your wall without having to fill the entire wall. This applies not just to buildings, but to everything else as well. So whether you're connecting things together or you're building Jersey barriers, all kinds of things, you can put in your vertical reinforcement that way. And your horizontal reinforcement is even easier. You just lay it down while you're printing. Because when it comes to rebar specifically, you don't have to tie them together. The ties are for making sure that they're in the right positions and that they're touching. So if you can actually lay everything down while you're printing, you know exactly where all of that stuff is because you placed it there. And it's basically as simple as someone just walks in, sets it into the wet concrete, walks out. So how you do this is you come up with designs, right? Just like you would in normal construction. You have your 3D model, only now it's divided into layers. So you say layer 9 needs 2 number 4 rebars in these specific locations, and you just lay them in. Constructability. So everyone always talks with buildings, they talk about printing buildings, but it's really the walls. So how do you deal with everything else? So we've printed 2 different buildings, and the first building, we had a slab poured. We dealt with how do we anchor it afterwards. We then built the rectangular building on top, put on a wood truss roof, which was very conventional, and then had a completed building. You can do it that way, but there's all different ways you can do it, just like there is in normal construction. Our second building, we still had a slab, but we put in anchor points while making the slab so that once we were done printing, we could easily tie the whole structure together. This building, which I'll talk about a little bit later, has a complicated geometry, but at the top it just goes straight. And so we could tie in a concrete, poured roof, essentially, that we used formwork with, and just tie those in that way. And so when you talk about construction, you really can mix and match all the different kinds of construction you typically do for construction. And this applies across the gamut from everything from buildings to bridges to other infrastructure. So now components. So we've, in the past, printed components for testing our finished buildings. And so this is one example of where we had our first military demonstration where we invited Marines to come to Champaign, and they printed 8 wall sections that are 6 feet tall and different designs, and they printed them in 8 hours after printing for only 1 day. So that's 8 hours total to print 6 walls. And then with this, we were able to test those wall sections to determine the best kind of wall before we printed the full building. And so we've done a number of things as far as structural testing, and if you have any questions on structural testing, Eric is sitting in the front here. He's also from Searle. You can ask him about those because he will give you a much better answer. But we've done everything from testing different reinforced polymer beams all the way up to testing full length. I think they were 16-foot beams. And we've also tested the wall sections we talked about here in different kinds of manners. And really what this all comes down to is we don't have to use formwork anymore. So if you can eliminate the formwork for your concrete, you eliminate a lot of the cost of materials associated with construction with concrete materials. And so in this, we built these walls, which we call chevron walls. The chevron walls have a zigzag structure on the bottom, and they go up to a straight wall at the top. And the reason for that is, one, that when you're tying in the roof, you don't have to deal with some crazy geometry on the roof line. You can just attach it to a stereotypical roof. The second is, it makes it a stronger wall that is also self-stable. So when we think about a zigzag type structure like that, you can now extend this wall as long as you want and change the kind of angles and the sizes of your buildings without having it to be re-engineered because it's a self-stable wall. And so when we did this, we tested these wall sections, and they were found to be 2.5 times stronger than straight 3D printed walls. And so when you start talking about those kind of numbers where you can increase the strength with only about 10% more materials, if even that, suddenly you can create buildings that potentially are hurricane resistant, tornado resistant. You can create structures that are just strong and much better than what's already being made. And since we're just in the cusp of this development, this is really just the beginning of where we can go. So we printed this building in 14 print hours. Now you might say, how many weeks did it take you to do, right? We essentially did this in 48 straight hours. Like, we came in one day, we left 2 days later, there were walls there. This north wall here, that's this wall over here, we printed from the bottom to the top. So this whole building was printed in 2 halves. And we printed this building from the ground all the way up to the top of the roof line. And the reason for that is, one, everyone always says that gantry type 3D printers, which are the normal structure for a 3D printer, can't print anything bigger than its envelope, right? But it can if you print it in sections. And so we printed a building that was twice the size of our printer by printing it in 2 halves. And with this, we were able to print all the way to the top, which shows that the limit is not the material, right? Its limit is people and machinery and just comprehending the process. A lot of people around the world, because they use mortars and paste, they have to deal with having a high slump material. And so in that, if they put consecutive layers on consecutive layers of wet concrete, it eventually slumps off and it fails. with our material, when we print, to make something that's as large as this, which is 16 foot by 32 foot by 9¼ foot tall, to print something that big in one layer, by the time we come around for that next layer, it's been about 4 minutes or so, and the material is set up just enough that it can support that next layer. And so if you feel about 6 layers down, it feels very firm. It feels like the concrete's already gone through some of its initial set. So we don't have to worry about how fast can we print as long as we give enough time for the material to get that initial set. And we also don't have to worry about the cold joints. So people that use rapid setting materials, what'll happen is if they go through and they print a layer and it's already cured before they come back and print another layer on, that material will not bind to the next layer as much. And so you have a weak spot. If you say leave your material and come back a week later, it's the same kind of thing. You have a cold joint there where you wouldn't have it if you printed it continuously. And so this building is really the first in the world that was printed in a continuous type fashion. And that is a huge push forward for the 3D printing construction field because it shows that we don't need to be limited by that time per layer mindset. And so with this, we are able to train Marines how to do this, and they printed, their very first print was this building. So we trained them while printing a building. And what we did is we then put reinforcement through these cavities in here. We just cast in those small cavities, so that whole wall isn't solid, just where the reinforcement is. We anchored them to the foundation, and then we had the Marines also build formwork for the roof. Conventional cast roof. It took longer for them to build the formwork for the roofs than it took for us to print the walls. And I don't mean by a little bit. I mean, we basically printed that building in 48 hours, and the roofs took weeks to do. So when you start talking about the speed of construction, that's where it really takes effect, is if you don't have to build formwork, that reduces the amount of time it takes to construct a concrete building or other structure. So what we did in December is we did a, this was more of a pre-print type situation where we printed just slightly away from where we were setting up this bridge. We printed the first 3D printed bridge in the Americas of any kind. And we did this with Marines down in Camp Pendleton, California. So we did it with materials that were not our home-based materials. We found new materials down in California, did some recon down there, and made up a mixture and printed with it. And so this bridge, we printed it and placed it in 6 days. That's 6 days from when we first started printing it to the point we are standing on this in this picture was 6 days. So some of those items maybe had 4 days to cure before we stood on it. Some of them, they had a full 6. And so what we did is we printed 3 different, what we call bridge beam sections, which is essentially like a double T. In this, we placed them with a crane with 2 piers that we also 3D printed and then attached them together. And from this, we used existing construction equipment. We used existing cranes, we used an existing Navy CB continuous mixer. We got all kinds of news coverage based on this as far as the first 3D printed bridge in the Americas. And so it didn't end there. We still had to structurally test this bridge because we only made it for pedestrians. And we specifically told them not to drive any vehicles over it because they hadn't been tested yet. Now, what we did then is we broke the first 3D printed bridge in the Americas. So we transported all of the beams from the bridge back to Champaign, Illinois, and we broke them. And we just did that a couple weeks ago. And in that, we had estimated they'd be about 15,000 pounds of strength. And in their testing, they actually came out to 45,000. because of the printed geometries. So when you start thinking about that, you can make objects that are stronger just with the inherent nature of 3D printing, with how you have layers and how it fails along different kinds of boundaries. And from this, we essentially can make a vehicle bridge with those kind of numbers. And so our next kind of step is to start trying to figure out how do we design this for vehicles and how do we get to that point and test it. And so over the next year, you'll see lots of news coverage about that. Basically, the objective is to support the weight of a tank. Not because we want to support a tank, but because if you can support a tank, you can support anything else below a tank. And with that, it improves mobility for all kinds of regions as far as if you have a disaster area where all the bridges were blown out, you can then print these temporary bridges, or if you want to make them permanent, you could, and put them up in areas that may get hit with another hurricane or all different kinds of disasters, and set these up so that emergency vehicles can get through, get them to people who need help. You can set them up so that people can get back to work if they need to get back to work. And you can do these, for civilian applications as well as military as well as disaster. So you think about if there's not a lot of bridges in Illinois that are vital, but if there's some areas where if a bridge is closed for a day, it impacts the area dramatically because that might be the only bridge to get to the other part, unless you want to drive an hour out of your way to get there. I used to live in Houghton, Michigan, which is where Michigan Tech is. And up there, there's one bridge that goes from Houghton to Hancock. And we used to live in Hancock. And school was in Houghton. And there were days that the bridge was down for maintenance. You couldn't get to school. And so when you start talking about how gap crossings affect people's lives, they have a very direct and almost instant reaction to when these kind of crossings go down. So this is really the first step. Like I said, first in the Americas, but it's not the last. And so as you see this technology develop, you're going to see more and more of these types of structures come out, which will be stronger and prettier and have all different kinds of new characteristics not typically associated with bridges. Now the big question everyone asks is cost. So how much do these things cost? Well, we've looked at the cost compared to a typical building made in both the CMU fashion as well as concrete. And you can see from the chart up here. You can ask Eric questions about this as well because he's the person who actually did this analysis. But basically what comes out of this is we've got ACC forms. So this is additive concrete construction forms. So that is basically you're making the form work for a building. This one is reinforced additive construction, like in a chevron. So that's like the second building we did. So it's basically like the first building and the second building we did. And with that, you can see that compared to CMU block construction, the additive construction is actually cheaper than building a CMU block construction like you're standing in right now. And this includes everything from the roof and the foundation as well as the walls, I believe. And so we're not just talking about the walls, we're talking about the whole construction in general. And when you compare additive construction to cast in place concrete, it's also cheaper. So what we're talking about is it's cost competitive with the existing conventional techniques. As it becomes more accepted and people have figured out how to do a lot more of how do we get the electricity into a building, how do we get water, once we figure those things out, this really becomes a real technology that people are gonna start considering. And so basically in summary, this is kind of the timeline. So I fed you guys a lot of information, right? Remember, I started this at about 4 years ago, right? And I've been involved since the beginning for our program. So we started out by building a full-size 3D printer that had the capabilities of basically 20 foot by 40 foot by 10 foot. And we built that all in-house with our own people. And then we moved to print the first structure. So we printed this small, we call it a guard shack, a guard shack or an entry control point, which is about 6 foot by 6 foot by 8 foot tall. We printed that as kind of our test of, can we print vertically? From there, like I discussed before, we printed the first 3D printed full-size concrete building in the US. We then printed wall structures in 2017 in order to test the building that we would print in 2018. We did a demonstration down at Fort Leonard Wood with soldiers and trained them how to use this technology. And then the end of last year, just in December, is when we printed the bridge, and then the bridge testing was done just a few weeks ago. So when we start talking about this timeline of how fast is this technology evolving, and is this change going to happen in the next 5 to 10 years? I mean, if you see how far we've come in 4 years, imagine how far we'll come in another 4 years, and another 5 years. And you can start to see the 3D printing and construction's effect because you see these companies start popping up. So there's several companies that have started producing 3D printers in this last year, as well as several companies who are starting to offer services for 3D printing with concrete and other materials. And when you start seeing these trends of how these small startups are trying to get into the industry, you can kind of make an expectation that in the next 5 years, you're going to see a lot of changes. Because if one group can do this much, imagine how much 20 groups could do in 4 years, especially if they're working together. And so when we talk about the benefits, we can reduce the cost compared to conventional construction by about 40%, depending on what kind of structure it is. You can reduce the time it takes to construct by about 50%, depending on the structure. You can reduce materials by about 44%. And these are all based off of a stereotypical rectangular type building. You can make 2.5 times stronger walls, at least, right? That's one data point we have for what kinds of structures we can make. You can make 10 times improved energy performance for buildings. So you can make cavities where you want there to be cavities. You can put insulation where you want there to be insulation. You can make structures more energy efficient because you have less seams, less gaps in your building, and you can make it use less electricity and less fuel. You can reduce the amount of people that it takes to build a building by about 4, if we're talking about a normal rectangular building. And you can reduce the hard labor involved. So since I'm part of a research group, we're all researchers. We have not been building things for a ridiculously long time and aren't used to mixing concrete day in, day out, most of us. And so when you start talking about how can we make it easier for people who are not typically hard labor type workers to build a building, I'm trying to make it easier for my team as well. Because if we can do more as a team, we can do more for the nation. And with that, you reduce the amount of injuries associated with that kind of work, because if you're not having to build formwork and use saws, do all that kind of stuff, you've eliminated a lot of the risks associated with construction. And we also have a couple journal articles that are coming out in the Additive Manufacturing Journal if you want more details on how all these calculations have been calculated. And in this slideshow, there were references to those journal articles as well. And so with that, I really just want to say it was a pleasure to be here today, and thank you guys for inviting me. And does anyone have any questions? Because I love questions.
I do have one. Thank you for this very nice presentation. I didn't know anything about 3D printing, and now I think it's added to my knowledge. But I have one question. I'm not a concrete expert, but usually, whenever you were showing the bridge, and then you said, okay, we did the bridge, and then we took it after how many? Maybe like a few months. You broke it, right? And then you checked the strength. But the entire premise is, I think, of the printing is to do it fast, right? And then the strength, of course, of whenever you're testing it and just allowing people to go over it is different from whenever you took it and tested after a certain period of time. So how are you accounting for that? And another question is, so you're not using any cast, right? There is no cast. So
Correct.
what's the type of concrete that you like? What are the additives that you usually add to this concrete to be able to cure to settle that fast?
Sure. So your first question about strength is you calculate the strength typical to concrete. And so when we all stood on that bridge, we knew that those bridge beams could support approximately 5,000 pounds each of load. So we definitely didn't go anywhere near that number with the amount of people that were on it. And the reason that we went on it was we weren't actually planning on standing on it in California because of that reason, but we had so many requests from the Marines to walk across it and to stand on it that we went through and we did the calculation to see whether it could support the load with only 6 days of cure time for some of those and less for others. And since the load that it could potentially support was much greater than what we were putting on it, we figured that it would be all right. We kind of did a safety assessment of that. And if anyone's tried to tell a Marine or a soldier no on something they really want, I don't want to be that person. So we definitely did it basically to show that it could support that weight that fast. The concrete we use is a fairly conventional concrete, sand, gravel. We use water, of course, and cement. So we use Portland cement. We put a couple traditional additives that we don't typically say that in kind of like a broadcasting manner, but we do have a patent that you can reference the details of the patent on there. We use conventional additives, and the amount of additives that we put in there is very minor compared to the mix. So the whole premises of what we do is that we don't want to bring stuff with us when we build, because if we're building overseas or anywhere around the world, we want to be able to get concrete wherever we go. And so that's why we do demonstrations around the US, is how little can we take with us. And so the only things that we took with us to California as well as Missouri were a couple buckets of additives for the whole print time that we were there. So I'm not going to get into details of the specific additives, but you can look them up in our patent if you Google it. So yes. Any other questions? Yes.
So in military applications, the productivity or how fast you construct those buildings or the walls can be a critical issue, I think. So actually, when you actually construct the bridges, did you use more than one printers or just one?
So for everything that I've shown you, we've just used one printer for. We have currently 6 different large-scale 3D printers at our facility, but we only take one of them when we go to a site. And so for the bridge, we printed with one machine, and our build area of that machine at that time was 8 foot by 16 foot by 10 foot approximately. And so we printed all those sections in there, and our machine is mobile enough. I forgot to mention that part. Our machine is mobile enough that, say, if I wanted to print something the size of this table, I can print this table, and then I can move the whole printer this way in about 10 minutes and print a whole other table here, and then move the whole printer that way and print another. So we printed 2 of the bridge beams at the same time, moved it over, printed another 2 just so we had 1 extra, and then printed the piers. So if you have more printers, you can definitely increase the amount of print time. Like if you think of the building that we created in 2 halves, you could have 2 printers going at the same time. And that actually makes the whole 3D printing process easier for concrete, because one of the big limitations of concrete 3D printing is that if you were to take like a concrete truck full of concrete, it would all set before you could get to it. Or at least it would set up enough that it wouldn't print nicely. So if you have 2 printers with 2 different pumps,
Right.
you can fill both those pumps at the same time and print something much faster. So yes, that having multiple printers would definitely add a lot more speediest construction for military applications, absolutely, as well as in the US as well. So.
Can you show us a photo or a video of the printer?
I can. I think. Let's see.
Do you have any on the website?
I do. So the printer. This is one of the printers we use right here. It's kind of hard to see. We do have some on the website. If you look up I think if you look up U.S. Army 3D printer or U.S. Army or Marines 3D printing concrete, if you look up any of the something that has Marines or Army and concrete 3D printing, you'll see pictures of the printer itself. It's basically a truss structure that looks like just a normal gantry. Like you could use a gantry crane in a high bay for something like this. And then we have a pump off to the side that feeds it through a hose which goes to a nozzle. Let me see if there's any.
How much pressure do you have to pump that concrete?
So it's a typical concrete pump. It usually operates, I think, about like 200 psi. So it's not a lot. Yes.
Oh, sorry. Excellent presentation. Thanks so much. I was wondering along the lines that you were just talking about, if there is a future maybe in concrete pavement applications like slip form paving with 3D printing?
Absolutely. So one of the big benefits of 3D printing as far as concrete goes is you can leave cavities. So if you think about slip forming applications where you're creating like a giant chunk of concrete as you go, you could either apply that same concept to 3D printing and create giant chunks of concrete, which is our next kind of research goal here, as well as if you start integrating layers and different geometries inside instead of the typical slip forming, you'd use less material and have the same kind of effect. Like if you think about curbs, do curbs actually need that much concrete on the inside? Or is it more of the external geometry that you care about? And so if you can design things in a different way, you can absolutely use 3D printing for things like slip forming applications. Yes, it's the same kind of principle, but much more 3D.
And you think the strength would increase maybe for better load taken and thinner slabs? I don't know.
Potentially. It depends on how you engineered it. So if you engineer it with truss structures on the inside that can take up that strength that would normally be taken up by just the volume of material, you can design those truss structures to be stronger. Or you can put different materials in those cavities to create more of a composite material. It really just depends on what exactly you're making, but absolutely you could create a similar strength or stronger structure with less material or different design applications. Yes.
Thank you for the presentation. So you stated a lot about the hype in this technology. So, in your opinion, what is this technology missing, and what needs to be developed so that we can reach all these goals that are treated as a hype right now?
So what's missing in the industry right now? A lot of the people involved in the industry are very focused on materials that are not accepted as structural materials. So things like mortars that are typically applied between CMU block or bricks. They're trying to print with that. And even if it's as strong, there's hesitance from the industry because it's the construction industry. Changing materials is always one of those things that it's hesitant. Everyone's hesitant on it, especially when you apply it to buildings or bridges or something that people walk through or drive over where there's a lot of risk involved. And so getting to the point where you can get just the method in and accepted is the first hurdle. So trying to get buildings approved by building code officials is part of that as well, is that we need structural engineers able to sign off on a lot of the buildings and structures that we've made, which is why we worked with Skid Moorings and Merrill to design that second building. The real gap in the industry is a lot of the work is being done on the small scale for concrete. So it's just using the paste and the mortars to try to print small structures and to look at the different print type designs. But really, to get it accepted in industry, you have to print components, large components, and get them tested and show these are structural components. These are something that can be approved for the general public to use. And so in that, there's a lot of work that has to be done in material development as far as making the existing concrete pumping technology applicable to 3D printing. So there's kind of a different thought process with concrete materials from the conventional. So when you're looking at concrete materials, you want it to have in the typical construction industry. You want it to have a certain strength and you want it to have a certain slump. And those are your main concerns when you're making a slab. In 3D printing, you're now looking at, does it have shape stability on its own? Can it just extrude and stay in that shape until the next layer is put down on it? It still has to be pumpable though. So you still need a decently high slump or a lot of flowability of your material to get it through those systems. And so a lot of the pumping systems that are out there are designed for very fluid mixes, or they're very large pipes to handle the more viscous materials. And when you try to print smaller structures or try to have smaller beads, all of that stuff is kind of fights each other a little bit. And so you have to develop these technologies in order to allow 3D printing to be better. So there's a couple aspects of that. One is the material work needs to be done on a full scale in addition to work in the lab, as well as developing the standards in that process for the full components. And the technology for the general concrete industry needs to just make a couple tweaks in order to be able to really be applicable to 3D printing for concrete. And then after all that, you still have to actually get these things out there and start using them and get people interested in them. I mean, I've heard a lot of people say I'd live in a 3D printed house as long as it looked nice and it still functioned the same, especially if it only costs $10,000. And so when you start talking about how is the hype setting us back, really it's just giving us way too inflated expectations. If you tell someone you can have a house for $10,000, and I come back and tell you, well, it's actually going to cost you $50,000, you go, I don't want to pay $50,000. But if you look at houses around, Champaign, you're like, oh, this house is going to cost $200,000. I can maybe build you a house for $100,000 that's just as big and nice as the first one. Suddenly you're going, that sounds a lot more reasonable. And then you have to start going into, can I actually get a mortgage for this house? Which is another battle that has to be fought. So there's all kinds of different hurdles that the technology has to get through, but there's enough buy-in from the people closest to this technology, as far as construction firms and owners that want to buy these houses, that they're pushing for these changes to happen. And so the one that will hold us back the most, I think, is the materials as well as the pumping equipment, for sure. As long as we can get buy-in from the structural engineers. So, yeah. Did that answer your question?
Yeah. So
Okay.
pumping and materials are the primary.
Concrete materials
Okay.
and the pumping technology.
Okay.
Yes.
So for the applications that are related to the army, I see why concrete can be the main material of interest. But let's suppose that this has become a tool for the military and we want to use it as for any for the public. So usually you'll need a shift from, because wood will not work anymore, right?
Mm-hmm.
I mean, there will be a shift towards concrete if it's. How do you see that?
So it's
If
really
it's for the public.
Yep. So it's really one of those things that you have to down select from. So if you want a 3D printed house, it can be made out of these following materials, which there's people working on polymers, so printing out of plastic at large scale. There's people printing out of foam at large scale, as well as concrete. And metal as well. But if someone wants a typical wood house, it would be difficult to do that. But that doesn't mean the inside of it couldn't be finished out like a wood house. But if you think about, it comes down to, it would be like you're normally picking out a building. So if you want it made out of wood, specifically wood, timber built house, you would say, okay, I have to get this built conventionally. Or robotically, if you have robotic capabilities to build your house. If you want it built out of concrete, you could then down select from the existing methods for concrete. If you want it built out of CMU block, you can down select from those methods. Like right now, CMU block has typical CMU construction, as well as there's robotic CMU block construction now. Like it's still in the very small early stages, but now there's robots that will lay CMU blocks out instead of having to be laid out manually. Same with bricks. So it's one of those things where, like, if you want a timber built house, it's going to be it would be very difficult to, right now at least, to print out of wood unless you wanted like a wood polymer type structure. Or, you know, if you live in a hurricane area, you might not want a timber built house. You might want a concrete house because those ones will last storms, they'll last surges. Some of the recent hurricanes, they said the only buildings that were left standing were the concrete ones. And so if you start thinking about down selecting how you want your house to behave, then you can determine what kind of method to use. Because like I said, 3D printing is only a method for creating buildings or other infrastructure. And I think that gets lost a lot when people start talking about it as 3D printing can change the world. Well, it's a new method, so the method can change how things have typically been done. And yes, it will change different aspects of the construction industry, but there's still a place for all the existing methods as well.
Thank you.
Okay, we ran out of time. Long time ago.
Yeah, we have a meet and greet session.
Yeah, let's thank Megan, please. So please jump.
And
It depends on. There, for half hour.
yeah, but now,
Yeah, right now.
guys, we have a
Figure it out now.
we have now.
Thank you very, very much.
Yes, you're
Let's
welcome.
have a meet and greet
Bro,
session.
we're just gonna get together with students.
Where's the meet and greet? Is it
Here,
here?
here,
Okay.
we're just gonna move some tables around and.
Okay. Sounds good.
So what we usually do is like the speaker speaks here, and then we sit
Okay,
at the
okay.
bench.
Attacked without questions. So many questions.
We asked so many questions.
Lisa, would you let me know when you guys are ready?
Yeah, sure. So let's first introduce ourselves. Let's start with Puneet.
Okay. Hi, I'm Puneet. I'm a PhD student and working in the materials group with Professor Akari. So